All right then. So now again, we are given the differential equation. All we need to do is to actually determine the general solution. And here, after determining the general solution, we're going to determine the particular solution. Let us read the statement first. The statement says to us, find the particular solution, not the general, of the differential equation, which is provided to be this one, given that x is equals to 1 and y is equals to 1. So now, in order for us to determine the particular solution, we need to determine the general solution first. But the question is, which technique are we going to use to determine the general solution of this differential equation? Honestly, we really cannot use separable variables from the get-go. But having a look at this equation, I can also again use homogeneous first order ordinary differential equations. So why? Because I can see I can divide both sides by x, y, whatever the case may be, and therefore I'll end up with something positive. But remember, what will be the standard form of differential equation? It's going to be dy over dx will be equals to p of two function x, y, and therefore maybe the function q here, x, y. This is the standard form on how to write the homogeneous first order differential equation. Remember, these two functions p and q supposed to have the same degree. So in order for us to write this equation in this standard form, what are we going to do? Let us let du on this side of the equation as it is, and then we divide by x to the power of 2 plus y to the power of 2, and then this side we divide by dy, dx, and therefore on this side that means we're going to have xy divided by x squared plus y squared. Are these two algebraic functions homogeneous? Yes, they are. Remember, when you have two functions multiplied together, you can just add the exponents, even though they are unlike terms, but you can add their exponents still. This is 1, this is 1, it's going to be 2. So the degree of the function at the top, it's 2, and therefore look at the degree of x squared, it's 2. Look at the degree of y squared, it's 2. So that means they have degree of 2, these two functions, for x and y. And therefore now we can perform the homogeneous first order ODEs. So in order for us to do that, remember the first thing we let, right? But what are we letting? We're going to have to let y to be equals to vx. Differentiate this. We're going to have dy in respect to x, dy over dx. Product rule, we keep v the same. Derive x is going to be 1. And then this side, we keep x the same. We're going to have dv over dx. Okay? So we let when you use the homogeneous. And therefore, this will be it. Now, what are we going to do? We're going to perform substitution. So where we see dy over dx, we substitute that. So that means on this side of the equation, you're going to have v plus x multiplied by dv and divide by dx, which will be equals to, remember, where you see y, you're going to substitute vx, right? So that means you're going to have vx is going to be x multiplied by vxx. We're going to have x squared there multiplied by v divide by, and then at the bottom where we see y again, we're going to substitute that. We see x, we're just going to write it as it is. And therefore we see y, we're going to have v squared and x squared, right? Now, here we're going to have, I'm going to transpose v to the other side of the equation. I have x dv divide by dx, which will be equals to, I can see that when I factorize x squared outside of the bracket, it will cancel with that x squared over there, and then I'm going to have v divide by 1 plus v squared subtract v on this side of the equation. And therefore, I'm going to have x dv divided by dx will actually be equals to, let's add these two guys over here. I'm going to have v at the top. I'm going to have this multiplied by that. It will be negative v. This multiplied by that. It will be negative v v to the power of 3, right? Divide by 1 plus v to the power of 2. Right? So meaning this is how this side is actually going to look like, right? And therefore now I'm going to multiply by the reciprocal of this on that side so that I can separate my variables. Me doing this, that means here I'm gonna have 1 plus v to the power of 2 divide by this v, subtract that v. They're gonna leave, I'm gonna left with what? I'm gonna left with negative v to the power of 3 dv, which will be equals to this side. I'm gonna have 1 over x dx. Now I separated my variables, right? Right. Now, remember, after this step, after separating these variables, I'm going to have to integrate both sides of the equation, right? I'm going to have to integrate both sides of the equation. But the question is, which technique of integration am I actually going to use? This is just the direct integration, right? Which technique am I going to use to derive this? Let's have a look at this expression over here. We can use by parts. We can use just direct integration. Would I be able to use U substitution? If I decide to use my U substitution, which one is going to be U? If I let V to the power of 3 to be equals to my U, so that means at some point, I'm going to have to let this. So meaning U substitution, it really won't work. But the partial fractions can work. You can see that we can actually separate these two fractions over there, right? So that means in this case, what we're going to do is we have the integral of separating these two fractions over there. We're going to have, let me take my negative outside. We're going to have 1 over v to the power of 3, right? Plus v to the power of 2 divided by v to the power of 3. It's actually going to be 1 over v, close my bracket, dv, right? It will be equals to this side, which is the integral of 1 over x multiplied by dx. And therefore, from here, I'm going to separate my integrals, but it's fine. You can just integrate from here. Now, integrating this, we're going to have, let me write my negative over there. Here, I'm going to have negative ln. Let me see. I'm just checking something, okay? But be careful, remember, basically, instead of you going far, trying to do long things or long methods, just always know that if you have something like this, when you integrate something like this, where is it? When you integrate something like this, I want you to consider the exponent, okay? It's very important for you to take that into consideration. But we only do that when we have the, sorry, we're not gonna do integrating this. We can just use direct integration. Okay, let me rewrite it. I wanted to do it quick, but it's fine. You can just do it like this. Okay, this and that. Remember here we have dv, this and that. It will be negative integral of, if you do v to the power of -1, it really won't work. You're gonna get math error because you're gonna have 0, I think. So that means here we can just let it as it is, and then you're gonna have dv, this side you're gonna have the integral of 1 over x, and then dx, right? And therefore, now let us integrate this. So here we're gonna have negative, negative. There we have negative, right? Be careful. There we have the negative. So that means we're gonna have a negative. Okay, let me do this so that I can take this negative outside of there. So this plus 1 is gonna give us -2. So that means we're gonna have -1 over 2 v to the power of -2, I think, right? Yes, it's gonna be -2, close bracket, and then this one is just gonna have negative ln of v, which will be equals to ln of x plus c. Therefore, we're gonna have positive there, which is 1 over 2 v squared, right? But remember, sorry about that, v can be written, this equation can be written like this, y over x which is equals to v. So here we can have y over x, but because of the negative exponent, I can just write it as x squared over y squared, right? Subtract ln of our v, it's gonna be y over x will be equals to ln x plus c. And therefore, you can just multiply these two over there. And therefore, this will be the general equation. But remember, we are not looking for a general equation. Rather, we are looking for a particular solution. So that means where we see x and y, we substitute 1. So that means here we're going to have 1 over 2 when we substitute 1 over there. And then here we're going to have ln 1, right? We're going to have ln 1. We're going to have ln 1. And then on that side as well, we are also going to have ln 1, right? I believe we are all familiar with ln 1. We know how much does the ln 1 actually equals to, right? The ln 1, if you forgot, you can just type it on your calculator, which is 0, right? So let's prove it and see. Ln 1 is equals to 0. Yes, it's 0. So that means, oh, let's not forget c there. And therefore here we're going to have 1 over 2 is equals to c. Therefore, writing the particular solution of this, where is it? Remember here, it's a general solution, right? So that means we have x squared over 2y squared subtract ln y divided by x, which will be equals to ln of x plus 1 over 2. Now this is the particular solution without using it's not the general, it is c, but the particular solution, it has a solved value of c, and therefore this is where we left.